Hi there. What you see is the result of this simple model. This is a busy artificial life. And look at these beautiful cell-shaped formations. Changing the model parameters produces different self-organizing patterns. Look at this pretty creature. This cell is very strange. Bubbles are forming on its membrane continuously. The diversity of the formations is staggering. This worm likes to eat the blue cells. Too much eating seems bad for it. This cell has learned to teleport. This one seems to act like a catalyst enzyme. Everything you saw was resulted from variations of this simple model, which defines the attraction and repulsion relationships among four particle types. The code behind these self-organizing patterns is so simple, it will be shame not to try it. So open your laptop, create a new file and call it live.html. Open the file with a browser, then open it again with any text editor and place it on the left side of your screen. Type something and save it. Refresh the browser. If the text appears on the browser, we are ready to code. First, we must build the blueprint of our artificial world. It's a two-dimensional world, 500 by 500 pixels. The basic building block of our world is atoms. Each atom has position, velocity, and color. Here we define particle as the building block of our virtual world. Each particle is a pixel that has position, velocity, and color. We define a function to randomly set the initial positions of each particle, and define another function to instantiate a group of particles. Finally, define a function to visualize the particles and add the time dimension by updating our screen continuously. Okay, now the boilerplate part of our code is all set up. Above the update, type this to create 200 yellow particles. Currently, none of these particles interact with each other. We need to add some sort of interaction. Let's start with two particles at the beginning. Inside update, type a rule to set the interaction. But first, we must define the rule. Newton thought if we knew all the forces that act on us, we can predict our next state. He also discovered the gravitational law, in which all matter in the universe attract each other according to their mass and their distance. For simplicity, we assume all particles have a mass of 1 and we ignore the square root. In the code, set the initial force to 0 for both x and y dimensions. Call particle 0 A and particle number 1 B. Calculate the distance between A and B according to Pythagorean law. then calculate the attraction force and distribute the force on both dimensions. Update the X and Y positions according to the estimated force. Now hit save and refresh. You can see one particle is moving toward the other. In order for all particles to attract each other, add one for loop on top and another for loop below to repeat the rule for all the particles in the list. Here, change 0 to I and 1 to J. Now all particles attract each other. However, there is something wrong. According to Newton's second law, applying a force to something causes acceleration. Therefore, we must increment the velocity of the particles by the applied force and then change the positions according to the new velocity. Now, when the particles reach each other, they are so fast they can't stop immediately, so they oscillate back and forth. If we increase the number of the particles to 3, the complexity of their movements increases too. The more particles we have, the more difficult it is to predict their next position, unless we calculate all the affecting forces. To prevent particles from leaving the screen, type this code to reverse their direction once they hit the wall. At the atomic level, effects are generally localized. Therefore, we can limit the force range to 80, but this can be fine-tuned too. To reduce the velocity of the particles, multiply this part by 0.5. In the world of atoms, attraction is not the only force. There is repulsion too. This is easy. Just change the G parameter from negative to positive, and now all particles repel each other. Increase the yellow particles to 200 and add another 200 red particles. As you can see, the red particles don't interact yet. The rule we defined above is reusable for all the particle types. For example, if you want to create an attractive force between the red and yellow particles, type the rule as follows. And if you want to create a repulsive force, change the sign of the number. The number represents the G parameter, which controls the magnitude of the force. Let's type some rules for all particles and see what happens. First, let's make the red particles attract the red particles. Add another rule to make the yellow particles attract the red particles with a little force. Now the red particles move slowly because they are attracted by the yellow particles from all directions. Add another rule to make the red particles repel the yellow particles by a small force. The pattern is now self-organizing to a nucleus with a membrane because the close-by yellow particles are repelled by the red clusters. We can represent all these rules with this simple model of relations. Let's add 200 green particles and type some rules between the red, yellow and green particles. Look, some cells go through an intermediate stage before they become stable. Let's try this interesting model too. Look at this strange thing with a head, wings and a tail flying around. We haven't explicitly described this shape and its movement anywhere in our code. This thing emerges from all the particle interactions specified in this model. Also, without the simulations, it's very hard to predict these shape formations and their future states just from the model. This could be related to Stephen Wolfram's computational irreducibility concept. We can increase the number and the type of the interacting particles, but with JavaScript the frame rate decreases quickly. Therefore, I have made a similar project with C++. You can download the program and its source code here. Extract the zip file. You can find the executable inside the bin folder. Double-click on particlelife.exe. This screen should pop up. Through the parameters on the left, you can determine the attraction and the repulsion amount between different particles in real time. You can as well determine their force range. Just like a rock falls on the ground because of gravity, these particles fall onto each other because of the rules and relationships we have defined here. And as a result, they self-organize to interesting patterns. Life-like shapes and stories emerge. Life is made up of a large number of compounds, proteins and enzymes that are constantly interacting with each other, each with a different attraction and repulsion properties. The complexity of these interactions increases as we go from the level of atoms toward the level of cells and organs. It looks like a simple story is getting complicated more and more. You can write the details of a story yourself, but then the events of the story are already simulated in your brain, and now it's a part of your memory. Conversely, if you determine the relationship between the characters, various stories will emerge according to their initial locations. Each time you change the initial location of the characters, new and different stories emerge. For example, this simple model gives rise to these beautiful and stable cell formations most of the time. However, occasionally close-by cells merge, causing instability, and as a result, small moving things are formed. These little things keep making the cells unstable. Eventually, all cells merge, but the outcome is a very unstable formation which keeps forming these little things. Interestingly, according to scientists, in the moment after the Big Bang, the matter in the universe were not evenly distributed, but they were fluctuating. Denser areas merged earlier to form galaxies and planets. Perhaps if the density here was slightly offset, I would have been a millionaire, but I knew this universe is set up against me. Anyway, it's clear that simple rules can give rise to complex formations and stories. In contrast, our brain tries to find the connections and reverse engineer these complex formations and their parts based on the detectable data. In addition, our brain has the ability to re-simulate our mental model, and this enables us to reimagine the stories. The universe can be seen as a large brain made up of a large network of relations that are constantly getting updated. And in parallel, our brains are trying to model and understand the relevant relations, but we are not only watchers, but also doers. That means we are actively involved in updating the universe's network of relations. If you find this video interesting, please like, dislike, or comment your thoughts.